Introducing the method of cylindrical shells. This is another technique that helps us to do the calculation and find the integral for the volume of objects or regions that you're revolving about x-axis or y-axis. So again, these techniques supposed to help you to do the calculations a little bit faster and easier. Consider your object that is revolving about y-axis. Take a look at this cross-section. The cross-section is not exactly a washer. It is a cylinder. So we're going to use these small cylinders and then find the volume using them. So considering a cylinder, the length on x-axis is 0 to x, and the height is on the function f of x. F of x representing this curve that you're trying to revolve about y-axis. So the measurement between the curve and x-axis or y equal to 0 gives you the height f of x. But if we look at this cylinder in a traditional form, the base is basically 2 pi times x. So down here, if you look at the base, what is the length of this base? What's the length of this circle here? The length of this circle is 2 pi times x. The height is f of x. You have a thickness, which is delta x as well. So we're going to use all of these pieces of information and calculate the volume. But again, 2 pi x is the length of the base. Two pi x, as you remember, is the circumference of the circle or the length of the base or the length of the circle. F of x is the height. Then delta x, as it getting smaller and smaller, represented by dx, shows the thickness. Now, if you take the definite integral from a to b, you're basically calculating the volume of this solid. So this is the method of cylindrical shell. Now, suppose you have two curves, f of x and g of x. When you're revolving this region about y-axis, the shell's height can be written as f of x sub k star minus g of x sub k star. The shell radius is x sub k star. The volume of this small shell is 2 pi x sub k star times the height, which is f of x sub k star minus g of x sub k star times the thickness, which is delta x. So the circumference times the height times the thickness gives you the volume of the shell. Now, the volume of this object, 3D object or the solid, is 2 pi times the definite integral of radius times the height of the shell dx, or mathematically it is 2 pi the definite integral of x times f of x minus gx dx, as x ranges between a to b. So again, this is the method of cylindrical shell. We just need to identify the height, and using the axis of revolution, here, please pay attention. The axis of revolution or the axis that we are revolving the object with respect to is y, but the definite integral is dx. So again, these methods are supposed to help you calculate these volumes. On the exam, on the homework, if they specifically ask you to use washer method or shell method, you have to apply these methods. But sometimes it's easier to switch around. When you're finding the volume, sometimes it makes it easier to use washer method. Some other times it's easier to use the shell method, but the result of the volume must be exactly the same. So to simplify this, when you're integrating with respect to x and you're using, for example, the disk or washer method about x-axis, you have the definite integral of pi f of x squared minus g of x squared dx. The shell method about y-axis gives you the exact same dx. So integrating with respect to x using disk or washer method or shell method. For the disk method, you're revolving about x-axis. For the shell method, you're revolving about y-axis. In another case, when you're integrating with respect to y, for the disk or washer method, you're revolving about y-axis. And the volume is with respect to y. Shell method about x-axis gives you the exact same dy. So again, when you're finding the volume, you can switch around between disk method, washer method, or shell method. But please pay attention to the integral. Which integral is easier to calculate? That's the whole point. The region bounded by the curve y equals to square root of x, the x-axis, and the line x equals to 4, and it's revolved about the y-axis. To generate a solid, we want to find the volume of this solid. Since we just learned about the shell method, let us apply shell method. But feel free to check washer method as well, or the disk method as well, to feel more comfortable switching around between these two methods. So you have y equals to square root of x, which is your graph on top here. Then you have x-axis, which is just right here. You have line x equals to 4, which is this vertical line here. So applying the shell method, f of x, or the height of the shell, is square root of x. And down here, the interval of integration is in between 0 to 4. The shell radius is x. This is your object now. You're revolving this about y-axis. So we take this object, this region, and start revolving this about y-axis. So as you can see, when you're looking at the cross-section, the cross-sections are shells, cylindrical shells. Now let us set up the integral. The volume can be calculated the definite integral from a to b of 2 pi times the shell radius times the shell height with respect to x, which in turn is equal to the definite integral 0 to 4. Again, please pay attention. With respect to y-axis, everything written in terms of x. X is bounded between 0 and 4. The maximum x value is 4. It is 2 pi times x times square root of x dx. It's equal to 2 pi times the definite integral of x times x to power a half, which is x to power 3 halves dx. So you end up with 2 pi times 2/5 x to power 5 divided by 2, ranges between 0 to 4. So after you plug in 4, it becomes 128 pi divided by 5. So remember that 4 can be written as 2 squared. So when you write this guy as 2/5 x to power 5 over 2, it is 2 to the second. 5 divided by 2, you can cancel out 2 and 2. So you basically have 2/5, 2 to the power 5, or 32 times 2 divided by 5, which is 64 over 5. But please note that you have a 2 pi in front of it. So 2 pi times 64 divided by 5 gives you 128 pi divided by 5. So this is our method of cylindrical shell to calculate this volume. So in applying the method of cylindrical shell, we saw that we are taking these small cylindrical shells, finding their areas, 2 pi x, which is the circumference of the base. Then you multiply that by the height, which is f of x, and then multiply by the thickness to find the volume of these small shells, adding them together, which is basically using the Riemann sum, the limit of the Riemann sum, which is nothing but the definite integral. And if you have two curves like f of x and g of x, the volume of these small shells is 2 pi xk star times the difference between y values, f of x sub k star minus g of x sub k star delta x. And it basically gives us the volume, which is 2 pi, the definite integral of radius times the height of the shell with respect to x, as x ranges between a to b. So these are all revolution about y-axis. So that's how you have dx. In this question, let R be the region in the first quadrant again, bounded by the graph of y equals to square root of x minus 2, and the line y equals to 2. Find the volume of the solid generated when R is revolved about x-axis now, everybody. Very good. So now we are switching from y-axis to x-axis. Take a look. This is the object that we're seeing, right? Here you have y equals to square root of x minus 2. Y is equal to 2, which is this line here. It's in the first quadrant, so that's why we stop here. And we are revolving this guy about x-axis. And we want to apply the shell method. So this is your object, right? It's revolved about x-axis. So since it is revolved about x-axis, what is the formula that we're going to use? We need to write everything in terms of y. This curve, which is y equals to square root of x minus 2. If you raise both sides to the second power, y squared is x minus 2. So x is equal to 2 plus y squared. That's how you end up with this equation on this side. X is y squared plus 2. So again, applying the shell method around x-axis, make sure to write everything in terms of y. Very good. The circumference of the shell is 2 pi times y, everybody. This is the base. You look at the base down here. The circumference has a radius, which is y. So that's how you end up with 2 pi y. The length of this base is 2 pi. There is no x here. 2 pi times y. Perfect. So let us set up our formula. V is equal to definite integral 0 to 2. The maximum y value is 2 pi y, which is the circumference, times y squared plus 2, which is the height of the shell. Then you take the integral with respect to y. So the volume is equal to 2 pi, definite integral 0 to 2 of, well, let us distribute y into parentheses, y to the third plus 2y, then take the integral, which is much more easier. So you have 16 pi. Well, doing the calculation shouldn't be that difficult for you. This guy is equal to 2 pi times 1/4 y to the 4 plus y squared, and y ranges between 0 to 2. I'm not going to use 0 because both terms become 0. This guy is equal to 2 pi times 16 divided by 2 plus 4, or 2 pi times, I'm sorry, this is 4. Perfect. So you get 4 plus 4, or 8 times 2, or 16 pi. So this is the volume of this object using the cylindrical shell method. So again, always remember the method. The cylindrical shell method, you need the circumference of the shell times the height times the thickness, and the limit of the Riemann sum gives you the definite integral. And in general, if you have two curves, and if you're revolving your object about y-axis, shell method says, hey, the volume is 2 pi times the definite integral of x, f of x minus g of x, dx. If you're revolving about x-axis, then you have to write everything in terms of y. Another example for you. Let R be the region bounded by the curve y equals the square root of x, the line y equals to 1, and y-axis. Question says use shell method to find the volume of the solid generated when R is revolved about line x equals to -1/2. So x equals to -1/2 is parallel to y-axis, everybody. So this is your object. This is the region that you're checking. You have y equals to square root of x. You have horizontal line y equals to 1. And then we are revolving this about x equals to -1/2, which is this vertical line here. So it's not exactly y-axis, it's parallel to y-axis, but you have a distance here between x equals to -1/2 and y-axis itself. So the shell radius is x minus -1/2, which is x plus 1/2. This is the radius that you're looking at, and the height of the shell is 1 minus square root of x. So basically here you have the height, and down here you're looking at the circumference, which you need the radius. When you're rotating this guy about the line x equals to -1/2, this is the object that you can visualize. So the base of the cylinder or small cylinders are located here. The radius are x plus 1/2. So to find the circumference, you have to multiply 2 pi by x plus 1/2. And then the height, you have one larger y value minus the smaller y value, which is 1 minus square root of x. So first visualize your object, try to find the radius. It's not always x. Sometimes we have to shift it a little bit to the left or to the right, depending on the question. So the volume is the definite integral 0 to 1, 2 pi times the radius, which is x plus 1/2. 2 pi times the radius gives you the shell circumference or the length of the base times the height, which is 1 minus square root of x. Then you take the integral with respect to x. This line is parallel to y-axis. It's easier to remember this way if you would like. This guy can be written as 2 pi, the definite integral. Well, we're going to distribute x into parentheses. We're going to distribute 1/2 into parentheses, do a little bit of algebra. You get x minus x times square root of x. So I'm distributing x into parentheses here for you. That's how you end up with x to the power 3/2 plus 1/2 times 1. Now you distribute 1/2 into parentheses minus 1/2 times square root of x, or x to the power 1/2. Then you take the integral with respect to x. This is equal to 2 pi times 1/2 x squared minus 2/5 x to the power 5/2 plus 1/2 x minus 1/3 x to the power 3/2, and x ranges between 0 to 1. But again, since all terms, they have x 0 is equal to 0. Just plug in 1 and do the algebra. It becomes 8 pi divided by 15. So this is the volume of this 3D object. Okay, so we have the same curve, all right? We are taking this curve, y equals to square root of x, the line y equals to 1, and the y-axis. And then we want to use disk or washer method to find the volume of the solid generated when R is revolved about y equals to 1, which is parallel to x-axis. So what do we have here? This is our object, right? This is our region that we have. Y is 1, y is equal to square root of x. Then you have your y-axis, which is just right here. The intersection between these is the region that you saw here. Now you're revolving this about line y equals to 1 itself. You want to use the washer method, or in general, the disk method. First of all, the interval of integration is between 0 and 1. We look at this 2D object to analyze what's going on. The radius of this disk is 1 minus square root of y. This is just a radius on the right. Now, if you revolve this about y equals to 1, this is the object. You're revolving it about y equals to 1. So as you can see, it's not like a regular revolution that we have about x-axis or y-axis. It's above x-axis, as you can see. The integral is pi times the radius to the second power, which is 1 minus square root of x to the second dx. So remember that the disk method, when you are looking at the cross section is a disk. This is your A of x, area of the cross section. Which in this case is a disk. But when you're calculating the area of the disk or this circular object, this is pi r squared, right? But what is r? R is this distance between the curve and y equals to 1. Your curve here, if you look at this object down here, makes it a little bit easier. Here you have y equals to 1, and then you have square root of x. So 1 minus square root of x gives you the radius. R is 1 minus square root of x. Then you plug that into the formula, and then it becomes the definite integral of pi 1 minus 2 square root of x plus x dx, which is pi times x minus 4/3 x to the power 3/2 plus a half x squared 0 to 1, or pi over 6. Calculating the volume using the shell method and also the disk method. You could also calculate this integral using the shell method. So again, if the question specifies that which method they want you to do the calculation, apply that method. But on the homework, on the exam, if it doesn't specify the method, you can switch around between them. But again, remember that the final answer must be the same. The volume is fixed value. It doesn't change no matter which method you're applying.